Hello everyone. Today we are excited to introduce Warped Diffusion, a new way to use image diffusion models, originally meant for still images, to solve video editing challenges. These models typically process each frame independently, which can cause flickering, texture sticking, and other inconsistencies in videos. Warp diffusion fixes this by ensuring the model respects the natural motion between frames. Let's start with the problem. Most image diffusion models assume that each frame is independent, but in a video, frames are connected by time. When these models are applied independently to each frame, the output often suffers from flickering and texture repetition. Although video diffusion models exist, they are computationally expensive and hard to access. Warped diffusion aims to bridge this gap by adapting powerful image models for video tasks. Previous work, like How I Warped Your Noise, tried to fix video inconsistencies by transforming the input noise using optical flow. Optical flow here refers to a motion pattern that shows how pixel moves from one frame to another. The idea was that if you change the noise according to this motion, the output image would change in the same way, a property known as equivariance. However, models like Stable Diffusion XL don't naturally follow this rule, which leads to inconsistent frames in the video. The core intuition behind warp diffusion is to treat videos as a sequence of spatially warped images. Imagine an image as a continuous function, like a rubber sheet. When you pull or twist it, the deformation is smooth. A video is then a sequence of functions where each frame is generated by applying a spatial transformation to the previous frame. In simple terms, if you warp the noise, the output should warp in the same way. This is what we mean by equivariance.
Moving on to the method. In step A, we use a pre-trained diffusion model like SDXL to generate the first high-resolution output frame. The model takes in low-resolution input frames along with smooth Gaussian process noise. This type of noise is important because it can be spatially warped later for consistency. Then, in step B, we compute optical flow between consecutive input frames. This flow tells us how objects move across time and give us the spatial transformation Tj, which we'll use to warp the noise and keep future frames aligned. In step C, instead of sampling new noise for each frame, we warp the existing Gaussian process noise from the previous frame using the optical flow. Since GP noise is smooth, this warping preserves the correlation between frames, which helps us in reducing flicker. In step D, to further enforce temporal consistency, we introduce equivariant self-guidance during the denoising process. At each sampling step, the model compares output from warped noise with the expected warped output and adjusts accordingly. Think of this as a correlation loop that minimizes warping errors and ensures that each frame aligns with the spatial motion dictated by the optical flow. Equivariance guidance is a solution to ensure that when we warp the input noise, the resulting video frame follows the same transformation. Although image diffusion models like SDXL are naturally equivariant, we enforce this property during the denoising process. Here's how it works. During generation, we warp the noise from previous frame using optical flow, and when we also warp the previous output forward. If the new frame doesn't align with warped output, we compute a warping loss and adjust the model's output accordingly. This correction is applied at each sampling step, nudging the model to behave as if it were equivariant to motion. ESG, that is equivariant self guidance, is efficient, fully inference time, and crucial for avoiding flicker and texture misalignment across frames. Warp diffusion is tested on video in painting, where large regions are masked in each frame. Using SDXL fine tuned for image and painting and applying GP noise plus ESG at inference, the model successively fills in missing regions with temporal consistent content. As shown in the results, prior methods like fixed or resampled noise produce flickering or drifting textures. Wrap diffusion preserves structure across frames, making the reconstructed content look stable and natural throughout the video. Here we quantify performance using self-warping error, which measures how consistent each frame is with respect to previous frames under optical flow. Warp diffusion achieves near zero error, both in latent space and pixel space. Competing methods accumulate significant drift over time, even when using warp noise. This proves that ESG isn't just a visual trick, it enforces true frame to frame alignment measurable through precise error metrics. In the video super resolution task, the goal is to upscale low resolution video to high resolution without losing consistency. Results show high resolution frames that are sharp and temporally stable, while competing methods often flicker or shift textures. This demonstrates that warp diffusion generalizes beyond in painting, achieving consistency at much higher resolution. Quantitative results show that warp diffusion again achieves the lowest warping error in super resolution under both pixel space and latent space evaluation. Even under synthetic shift scenarios, it maintains alignment across frames better than all baselines.
Overall, this framework effectively transforms powerful image diffusion models into tools capable of generating high quality, temporally coherent videos. To sum up, warp diffusion is a novel framework that leverages noise warping and equivariance self guidance to adapt image diffusion models for video applications. It addresses the challenge of temporal inconsistency, providing smooth and realistic video outputs. This approach not only offers a practical solution using state of the art models, but also opens up avenues for further research in the video synthesis. Thank you.